Let's see. Last class we discussed up to the six ligand, six field systems in CFT. Once again, now it's all about four ligand system. Okay, if four ligands has to approach towards the central metal atom, we expect them to approach between the axis like this. As they approach between the axis, now the orbitals, d orbitals, which are oriented towards the axial directions, like you can see this particular orbital here, this one is dx square minus y square, and this one is dz square. Now these orbitals will get lesser repulsions, while the orbitals which are between the axis, like dxy, dyz, and dxz, they will experience more amount of repulsions as compared to that of dx square minus y square and dz square. Correct? So you can see these three orbitals are experiencing more repulsions this time. Secondly, unlike earlier cases where the ligands were approaching head on and giving a repulsion, a large amount of repulsion to the orbitals along the axis here, this time the ligands are not exactly coming in between at 45 degrees. So neither they are coming axially nor they are coming between the axis at a exact 45 degrees. So the amount of repulsion that they uh, that they give it on the d orbitals would be relatively less than what they give it in the octahedral cases. So tetrahedral will always have a lesser splitting. So you can see delta T, which is a lesser splitting, right? But still there is some amount of energy increase. And from there, you notice that this orbitals here, so the d orbitals here, will start either raising its energy to T2G and EG kind, which means again the redistribution would happen here. And EG set, EG means which orbitals? EG means dx square minus y square and dz square. These two orbitals, they would have relatively lower energy. dxy, dyz, and dxz. These will have higher energy or higher energy. Okay, clear? So now, if this is the energy diagram here, so this is the line, got it? Then these orbitals dxy, dyz, and dxz will have more amount of repulsions experienced as compared to that of dx square minus y square and dz square. Now we will drop one thing. We will be dropping this term g here. So we will not be using this term g anymore. Instead, we use it as E and T2. This subscript G here represents gerade. Gerade means a symmetry. The tetrahedral orbital does not have any symmetry on it. So that's why, since it is not forming any symmetrical orbitals, so this G is to be removed out of it. So now the orbital sets are called as E orbital and T2 orbital. Okay. And since E set orbital have now lower energy, how much will be each orbital having the energy? Because these three orbitals energy is now lost here. So that means it will be minus 3 by 2. And these two orbitals energy is gained here. So it is 2 by 5 delta T. See, when I use delta naught, that is for octahedral splitting. Okay. Delta T is for tetrahedral splitting. That is for tetrahedral splitting. Correct? Delta naught and delta T. So check. How much is the splitting energy here? So you can see From this zero line onwards, as you go up here, it will be 2 by 5 times of delta t. Here it is minus 3 by 5 times of delta t. Got it? Now, notice one thing. As I said, if this is the dxy orbital, the ligand is not exactly coming here as an head-on repulsion. It is coming from the side. So it will not be giving a huge amount of repulsion either. So we can say what would happen here is the two-third amount of repulsion is lost. Second thing, only, how many ligands are approaching? We are expecting four ligands, but only, sorry, we are expecting six ligands, but only four ligands are coming. So that into delta T. Got it? So what are these ratios exactly? This two-third is the lost energy, lost repulsion energy because of being a sideline ligands, not a head-on ligands. Second, this 4 by 6 represent that expected amount is 6 ligands. If 6 ligands come, if you imagine like X amount of repulsion will come. If only 4 ligands will come, 4 by 6 amount of repulsions will only come. So 4 by 6 it is. So now it will become total is 4 by 9 times of delta naught. That's what I have written. So that means delta T will be around 4 by 9 times less than that of delta naught. Okay. Which clearly suggests that this kind of splitting when you have four ligands is more applicable for cases where there are weak field ligands. For example, in this case, nickel Cl4 2 minus. If I put the primary valency in this case is 2. Secondary valency in this case is 4. Got it? Nickel is plus 2 oxidation state. So it is argon, 4 is 0, and 3d 8. And this d orbital has split into set of new orbitals. One is Eg, the other one is T2. So total we have D8 electrons. So 1, 2, and then I'll go here 3, 4, 5, 6, 7, 8. This is how the splitting should work. E and T2. These are the two sets of orbitals, and the splitting energy between them is delta T. Sorry. Now you know that this delta T value will always be less than pairing energy. Correct? Hence, electrons will less likely to be paired. Less likely to be paired. And since they are less likely to be paired, then 3D orbital is not available anymore. So this 3D orbital has the electrons in it. So that is not available for hybridization. 4s is empty. 4p is empty. So to accommodate these four chlorides, these are the orbitals I will use. 1, 2, 3, 4. This is where the chlorides electrons can go. So that makes it sp3. So therefore, this NiCl4 2 minus is an sp3 hybridized orbital. Hybridized orbital. Okay. Second, what is the other thing I can say? It is a tetrahedral geometry. It's a tetrahedral geometry. And next, you can see there are two unpaired electrons. So two unpaired electrons. Now I can precisely say which orbits also present in either dxy, dyz, or dxz orbitals. And I can definitely say that they are not present in dx square minus y square and dz square. Got it? And since there are unpaired electrons, so this would remain paramagnetic. So remain paramagnetic. Okay? Clear? Everybody, please check this out. This is how you need to figure out, how the tetrahedral complexes work. Here, everyone. So if at all we are using anything sp3, correct? Sp3 is also, we can call it as outer orbital complex. It is not necessarily always has to be with the d orbital. We can still call it as outer orbital complex. Okay, right. From here, I can say that whenever the ligands are approaching, if at all they are weak field ligands, correct, they can give less amount of splitting. That means we can naturally expect them to go for more tetrahedral geometry like this, more than square planar kind. Square planar is a case when you have strong field ligands. I'm talking about only 4 ligand system, guys. Okay. Now let's talk about square planar system. Okay. How do we need to see the square planar cases? Right. When it comes to square planar cases, imagine this way. The easy way to understand is like this. Imagine as if there are 6 ligands approaching. There are 6 ligands approaching. Got it? If there are 6 ligands approaching, they will try to be more of an octahedral kind. So that means initially, even the orbitals, when the ligand starts coming from the axial direction, there will be raise in the energy of the d orbitals due to repulsion. And then we can expect them to go and convert itself into T2G and EG type of splitting. We'll go into T2G and EG type of splitting. But now what happens? While this Z axis is waiting for this ligand 5 and ligand 6, that's never coming. So it will wait for some time till, the orbital will split, and they will wait for some time for other 2 ligands to come. But if they are not coming, now what will happen? The redistribution of these orbitals again take place. Now think about it carefully. Suppose if you have an orbital like the dx square minus y square orbital is like this. This is dx square minus y square orbital. Okay. Dx square minus y square orbital. This is x and y plane. So imagine this entire thing is the plane on which dxy plane, correct? And ligand is approaching on this plane only. So ligand 1, ligand 2, ligand 3, and ligand 4. So it is definitely giving an head-on repulsion. That means this dx square minus y square experiences the highest amount of repulsion. So that means from here again that splits, and dx square minus y square will have the highest amount of energy. And within this same space here, within this same plane here, you will see will be set of another orbital. What is this orbital now? This is dxy. If this is dx square minus y square, this is dxy. So now you notice that dxy will also experience more repulsions because they are pretty close to all these 4 ligands as they are on the same plane. So the next most repulsion will be for dxy. So from this orbital of T2G, this dxy will have more energy and that will rise. And next, you notice that if this is xy plane, so I'm writing the same xy plane here, guys. And imagine ligand 1, ligand 2, ligand 3, ligand 4 are approaching here, correct? Now, where is z-axis here? In this case, suppose if at all I write this as a plane here. So this entire thing is a plane, xy plane, okay? So on this xy plane, you will see that this direction we have z-axis. This is z-axis. And you know that along the z-axis, we will have dz square. This is dz square here. Like this, it will be dz square, correct? But we need to understand one thing. Along this dz square, z square, we actually not just have one lobe. It will also have a circular lobe here, like this. This is another circular lobe. And this circular lobe is present on circular lobe, circular lobe is on xy plane, is on xy plane. So therefore, these ligands will also repel that circular lobe. Hence, dz square will also have slightly more energy. But of course, relative to how much we are expecting, that much it will not have, but definitely more than the other orbitals. That is dyz and dxz. They will have least amount of repulsions. Hence, now this Eg and T2g is further splitting into set of four orbitals. The energy difference is delta 1, delta 2, delta 3 here. This is the energy difference what we have. So sum of these energy differences, right, together is what we call it as the square planar splitting energy. So square planar splitting energy will be equal to 1.3 times of delta naught. All good, everybody? This will be 1.3 times of delta naught. This is a value, you can just mug it up, that this much amount of, you can see there is much higher energy, higher amount of splitting compared to that of octahedral complex has been observed. So overall, splitting energies, if you compare, definitely delta Sp is more than delta naught is more than delta T. Done with that, everybody? Clear? So please look into it once quickly, how the square planar splitting happens. If there is any doubt, you can ask me. So let me show this example. Nickel cyanide with 2 minus. Primary valence is 2, secondary valence is 4, and it's a strong field ligand. So, which means the configuration, the nickel configuration here is nickel plus 2, which is argon 4s0 and 3d8. Now I can say that when it comes to 3d8 here, before the splitting, the distribution of d8 electrons is like this. This is before splitting. After splitting, now we have set of 4 new orbitals. That is these two. Then we have one. Then we have another one. And then we have another one. Okay. These two are dxz and dyz. This is dz square. This is dx square minus y square. Sorry, dxy. And this is dx square minus y square. Now let's distribute these electrons. First electron, second electron. Third electron, fourth electron. Fifth electron, sixth electron. Seventh electron and eighth electron. Got it? So now it is very much clear that only 3D x square minus y square orbital is available. 4s is empty. 4p is empty. So it will be utilizing these four orbitals and make this into dsp2 hybridization. That's how you get dsp2 hybridization. So now we know precisely in which orbitals we have how many electrons. Everyone clear? So after the distribution, you can notice that it is a diamagnetic molecule. Diamagnetic. It is using the inner d orbital, so it is inner orbital complex. Inner orbital complex. The unpaired electrons are decreasing, so that makes it low spin complex. So it's a low spin complex. Got it? And it is square planar geometry. Okay? Done? Right. These are the pointers that we need to know. So CFS is actually helping us to realize where exactly the electrons are going, which orbitals they are going. Correct? And in this case, if you can see, this is delta 1, this is delta 2, and this is delta 3. Okay. Delta I means 1, 2, 3 in this case is less than pairing energy, but sorry, greater than pairing energy. So that means in all these cases, first filling is important. It will follow Aufbau's rule. Sorry, fill all the inner electrons, I mean lower energy electrons first, then only go to the higher energy orbitals. Okay, so that's how it works. Clear? This is the square planar cases. Okay, so I hope this part is clear, everybody. Okay, right. Second. Second. Yeah, let me re-explain that. Color will basically have these colors in their increasing wavelength. V, I, B, G, B, G, Y, G, Y, O, R, P. These are the colors. Okay. In case if I got these four complexes A, B, C, D, and the question is to figure out what are the colors associated with it, given that I found four colors: red, blue, orange, and violet. So first thing what you do, you figure out what is the ligand strength. More the ligand strength, more is the splitting. More is the splitting, less is the wavelength absorbed. So if I label this as A, B, C, D, D has absorbed smallest wavelength, A has absorbed largest wavelength. So then now write the absorbed colors for these complementary colors. Absorbed colors are blue, red, blue, green, yellow, green. That is as per color wheel. Now arrange them in their increasing or decreasing wavelength. So this is their decreasing wavelength order. So since red is the color which is absorbed, so what is the complementary color which you are observing? Blue. So that means A is blue color. Similarly, B is YG, that means YG is the absorbed color. So what color it will appear? Violet color. C will appear red color and D will appear orange color. Right? So D is blue green. So blue green means it is orange color. Done. Same thing. What if I give you this next question, 1, 2, 3, this question here, and imagine I found three colors. Okay, correct. These are complementary colors. Complementary colors. The complementary colors I found are yellow, purple, okay, and let's say green. These are the three colors which has been observed. Correct. So I want you to figure out, clear, if these are the colors, what is their absorbed colors? Clear? What is their absorbed colors and which of these will belong to yellow, purple or green? Okay. So I'll give you a minute's time. Please try using color wheel and do it. So listen to this, everybody. If yellow, purple, green are the complementary colors, then indigo, green, purple are the absorbed colors. If I arrange them in their decreasing order of wavelength, that is purple greater than green greater than indigo. So since purple wavelength is highest, that means adsorbed light is lowest. So the lowest will be for here. So that purple is complementing green. So it should be green. Likewise, the rest will be purple and yellow. Okay. So this is what you need to learn from color wheel. Now, I hope you got an idea about during the DD transition, it is absorbing that light. Okay. The colors are even more intense and much more brilliant when there is a charge transfer happening with. Okay, but why is that so? In fact, a complex colors which are happening via charge transfer will be much more intense and brilliant as compared to that of complexes only showing DD transition. Why is this so? The reason is because of something called selection rule. This is because of something called selection rule. According to the colors theory, which explains that if the selection rule is followed, right, during the excitation or de-excitation of electrons, okay, if excitation or de-excitation of electrons, if the color rule is followed, then complexes which follow the color rules, that is selection rule, will always be more intense and brilliant. Now, what are those rules exactly? Check out. Any transition, that means any excitation or de-excitation of electrons, okay, so during excitation or de-excitation, in case if the change in azimuthal quantum number is plus or minus 1, that means the selection rule is followed. Got it? For example, imagine if an electron is present in 2s and it is transitioned into 4d. Is the selection rule followed here? No. This is not selection rule followed. Why? Because delta L value difference is 2. Suppose if you have 5p and it is going to 3d, whether it is excitation or de-excitation does not make any difference. Now this is a correct transition because delta L value is 1. Correct? So it could be plus 1, in fact minus 1 here. Okay? Right? So it could be, sorry, plus 1 here. Yeah. So 2 minus 1. Right? So that way, if it is plus 1 or minus 1, that means we say it is selection rule being followed. Okay. So you can see delta N value is plus or minus 1 here. Got it? Similarly, close the door. Okay. Next, sorry. If you have 3D, maybe de-exciting to 2p. Here also you will notice delta L value is minus 1. This is a correct transition. Okay. Now if it is going from 3D to 4D, then also it is not correct. If it is going to 3D to 3D, then also it is not a correct selection. Right? So that means if it is going from T2G to EG or EG to T2G, both of them are not correct. Both of them are not correct. Both of that means both of them are not following the Lepot's selection rule. Okay, so now you understood DD transition is not following Lepot's selection rule. Correct? Second rule. Second rule is spin selection rule. Spin selection rule means after excitation of electrons or de-excitation of electrons, the spin value should not change. So if spin value does not change, that means if plus half the spin of an electron was plus half, after exciting also it should remain plus half. Okay, that is, imagine if an electron is present here in T2G and it is exciting into, let's say these are the electrons present like this, and one of the electrons is exciting here. Okay, so after excitation, if that electron, that is after taking some light, it has excited here and reached here. So if the spin is the same here, so then we say it is following spin selection rule. So delta S is 0. Okay. But if you notice one more example here, let me write one more example in which suppose I already have few electrons here. 1, 2. Now the light is being given and electron is exciting here. So since electron is exciting now, it has to forcefully change because already there was a same spin electron present. So now what happens to delta S? Delta is actually 1 because that has, why it is 1? Because it was half of and now it has becoming minus half. So that makes it 1. So in that case, here we can say it is spin not followed. Not followed is called forbidden. Okay. Spin forbidden. So this transition is a spin forbidden. And T2G and EG are Laporte's forbidden. Laporte's forbidden. Right. So in case if there are any cases where both Laporte selection rule and spin selection rule, both of them are forbidden, naturally those complexes will have very pale colors. Very pale colors. Let me show you with one example. Example, if you see MnH2O 5 and 2 plus. Now in this case, this is a D5 electronic configuration. Sorry, 6 here. So there are 6 ligands, so which means it is a splitting of T2G and EG. And there are 5 electrons. So 1, 2, 3, 4, 5. So after the light has been, and it is going from T2G to EG. So you can see after the light approaches, after the light approaches here, so what happens to the complexes here? So after the light approaches, it will take the electron. One of the electron will go from here and go to the higher orbit, EG, and this is the situation right now. So I can say in this case, it is Laporte's forbidden because it is DD transition, and it is also spin forbidden because the spin of the excited electron has changed. That's the reason Mn plus 3 is pale pink color. Pale pink, or pink in books is written as buff, pale buff color. So the pale colors can be explained by the fact that both selections rule are been forbidden. Everybody understood? Now, what type of questions JE will ask? JE will ask for this type of question. A lot of time this question has been asked, that identify the correct transition possible. So you should be able to figure out any transition is given. All you need to check out is whether delta L is plus or minus 1 or not. Second thing, it might be asked which of the following are pale colors. Then what you will need to check out, you need to check out which of them are actually making a Laporte's as well as spin forbidden cases. All good, right? So I've written it here. That is pale pink color. Okay. Now let's understand how the charge transfer is making the colors more brilliant and more intense. Check out. In here, what is happening? An electron from ligand is going all the way to metal, and that is getting transferred from ligand to metal. For example, let me show you with example here. Suppose I have MnO4 minus. Okay. In this case, manganese is like a metal, and all oxygens are like ligands around it, like this, O minus. Now, suppose when the light approaches here, correct? So something like the light is coming here. So what will it do? Electrons present on the oxygen, they will absorb it and they will push the electrons towards manganese. Why is that? See, manganese is at a very high oxidation state, which is plus 7. So it has very high affinity to pull the electrons. And that is being helped by the light. As soon as the light falls, the electrons from oxygen will take up that energy and excite to manganese. And this energy difference, correct? So this energy absorb is found in visible region again. The difference is found in visible region. Got it? Now notice this one, everybody. The electrons present in oxygen are in 2p orbitals, and the empty orbitals present in manganese are 3d orbitals. In fact, 3d or 4d, both of them are empty here. Correct? So now the electron is going from 2p to 3d. So what is happening? Delta L value is 1. So which means it is Lepard's followed. Second thing, manganese plus 7 is kind of empty d orbital. Empty d orbital. And 2p orbital, which has electrons, if it goes here, no need to change the spin. So therefore, delta S is 0. So that means it is Lepard's followed as well as spin followed. So when charge transfer is happening from ligand to metal, we have clearly noticed that there is a Lepard's selection rule followed, there is a spin selection rule followed, which makes the colors very intense. That's the reason why MnO4 minus is, you know, intense purple color. Intense purple color. Okay, or distinct purple color. Clear now? So I hope you understood how the charge transfer works. Okay. So now you notice that charge transfer usually observed more often in higher oxidation states. Okay. So when it comes to higher oxidation states like KMnO4, K2Cr2O7, CrO3, MnO7, K2Cr4, V2O5, KMnO4, and all of this. Okay. V2O5 also has a color. I forgot that. Okay. So in all these cases, you will notice we will have mostly LMCT cases. Okay, because metal is higher oxidation state surrounded by oxygens. So Lepard selection rule is strictly followed. Okay. Last case is interesting. Iron plus 3 is the highest oxidation state iron can achieve. Okay. And that ligands SCN minus is pushing the electron. So that is also making a more than here DD transition is also happening. Remember that. I'm not discarding the fact that there is no DD happening here. So there is a DD transition also happening, but at the same time, the charge transfer will dominate it. So that's the reason why in these cases, LMCT is more observed. There's a very standard JE question, everybody. Which of the following will give you LMCT type of transition? So you should know it. Got it? Next one. Next one is MLCT. That means from metal, the electrons are transferred to ligand. So this time mostly delta L value will be -1. It doesn't matter whether it is +1 or -1, Lepots are followed. Okay. So now I can say that if electron are jumping from this to this here, so ligand must have an empty pi star orbital. Got it? Or empty d orbital. Either an empty pi star orbital or empty d orbital. If the ligand has that, then the electrons from metal can transfer. So that's the reason why you notice NiCO4, FeCO5, FeCO5NO, rhodium, triphenyl phosphine chloride. So in all of these cases, right, there is either a pi star orbital or an empty d orbital present on ligand, and from metal the electrons are being transferred, and that gives some intense colors. This kind of transition is called as MLCT. Last one is MMCT. MMCT is metal to metal charge transfer. Typically observed when you have complexes where inside and outside are also metals with high Z effective values. For example, iron plus 3, high Z effective, iron plus 2, high Z effective. Between these two, if the electrons are moving, that will also give you intense colors. What happens is electrons from mostly 3D jumps into empty 4p orbital like that. Okay. So from 3D, it will go to 4p orbital and vice versa. If that's the way the transition happens, it appears very brilliant color. Prussian blue color is a very brilliant color, very intense color. Everyone, please learn the examples carefully. That is, it is the examples which are more often asked. So check it out. What are the cases and what are the examples? Any doubt here? Earlier case, beta. Pratisha, should I explain again?
Yes, sir.
Right, one second. Right. So please check this out. Let's make a simple table here. Okay. So one, which are Laporte selection rule followed. Okay. The other one, spin selection rule followed or not followed, anything. Correct. And what is the type of spectrum? Type of spectrum. And last one, what are the examples? Okay. This is the idea we should have. First, imagine Laporte's followed or allowed. Laporte's allowed and spin is also allowed or followed, right? And that usually happens via charge transfer. In most cases, it is charge transfer. Examples: MnO4 minus, MnO4 2 minus, CrO3, CrO4 2 minus, got it? Cr2O7 2 minus, and even colors like CDS, AGI, correct? CUS, all of this. These are also fall into that cases. Okay, clear. So, second one, there are cases where there are partly followed. Partly followed. Okay. This partly followed is because their orbitals are not pure. They are usually PD mixing orbitals. So P and D mixed orbitals are present. And that spin is still allowed. That cases usually happen with DD transition. Cases like cobalt Cl4 2 minus, cobalt Br4 2 minus. Okay, clear. So this one. Next. Next one is completely forbidden cases. Completely forbidden cases. But this is allowed. That usually happens in DD transition with T2G, like T2G to EG जा रहा है, but EG में कोई electron नहीं है. When there is no electron in EG, like titanium, H2O3, sorry, H2O6, 3 plus, or chromium, NH36, 3 plus, or chromium, H2O6, 3 plus, and so on. These kind of examples. Okay. Next, partly allowed. Partly allowed here, correct? But spin is completely forbidden. Partly allowed, but this is completely forbidden, like in DD cases. So you can see MnCl4 2 minus and MnBr4 2 minus. These cases will have partly forbidden cases. Okay. See, when have you noticed something? Whenever I'm using the partly allowed cases, those are mostly sp3 hybridized ones, correct? So that means they are mostly having that partial P and D character together. Okay. For example, if both of them are completely forbidden, I give you the example already. So this is forbidden. This is also forbidden. Typically happens in DD transition. And best example is manganese, H2O5 and plus 2. Sorry, H2O6 and plus 2. Okay. So please make a note of this table, everybody. Important one. Okay. Yeah, I have to give you your injection. Okay. So wait, I will take the medicine then. When we go further, see, when it comes to colors due to LMCT, I gave you some examples. Got it? Now, these are part of an LMCT only, correct? But it is used in a different format. That is color due to polarization color due to polarization of anions. Polarization of anions. Okay. That means if the anion is easily able to push away electrons towards metal, then also you will see the colors coming across. Right, check. For instance, if you take AgCl, okay, AgCl is white in color because chlorine is slightly, I mean, it's not very big in size. It cannot polarize the electrons very easily, okay, towards the uh, silver. But when it comes to AgBr, AgBr is yellow in color. Got it? Okay. In fact, pale yellow in color. And why, when it comes to AgI, it is dark yellow or complete yellow. Why the color become intense here? Because I minus has more polarizing power, polarizability. So higher the polarizability, more easily electrons can push towards metal. That increases their colors. So therefore, when it comes to BiCl3 also, it appears white in color, while on the contrary, BiI3, if you notice, it is completely black in color. So you can see there is complete transfer here. Same PbCl2, PbBr2, and PbI2. PbI2. So if you notice these three also, you'll see PbCl2 is white in color. PbBr2 is also pale white, but in NCRT and lab manual, they have always considered it as white. And here we consider it as, I mean, PbI2 is actually yellow in color. Okay. Next, if you notice HgCl2, got it, and HgI2, same logic here also. HgCl2 is white in color, but HgI2 is scarlet red in color.
Sir, you are muted.
Oh, sorry. Okay. See, when it comes to these cases, polarizing power for these is quite high. Okay. When connected with sulfide or oxide cases. Got it? So that's why they'll have usually strong colors. For example, Cu2O, Cu2S, okay, or Cu3P, got it, or Cu3P2. If you compare all of them, you'll see this one is red, but rest all are black in color. Rest all are black in color. Okay. Okay. So you can see Cu2O is +1. So it does not have too much polarizing power. But the minute you get even CuO also, CuO is almost black in color. Correct. The same goes with silver cases also. So when it comes to silver, whether you take Ag2O, Ag2S, Ag3P, all of these are black in color because of high polarizing nature. Done. Got it? Right. Next, few more examples. Let me list out here examples of LMCT. Okay. Few more examples of LMCT because anything could be asked, so it's better to know all the cases thoroughly. Okay. Already I gave you some cases, that in case if it is being asked like this, Na2 FeCN5NO. This is also due to LMCT. Got it? SNI4 colored due to LMCT. PbCrO4 LMCT. PbO2 LMCT. FeBr3, FeCl3, FeSCN thrice. Okay. Cu2O or CuS. Like I said, all the polarizing cases will also considered as LMCT. Okay. Next one is MLCT. MLCT cases. When it comes to MLCT, notice that K4 FeCN6 metal to ligand charge transfer. NiCO4. Got it? FeCO5. Got it? You know that FeC5 H5, sorry, we'll write sigma pi, right? So pi C5 H5 twice. This is called ferrocene. So, okay, ferrocene. And same way, chromosine, that is C6 H6. I'm sure you remember this sandwich complexes. We discussed about the sandwich complexes. And FACAC thrice. Right. So, all these cases, by the way, these are all going to be MLCT cases. Metal to ligand charge transfer. Last one is MMCT cases. Metal to metal charge transfer. Okay. Right. Once again. Right. So, if you have cases like FeCN6 this way. Clear? Inside and outside, both of them are +3. Okay. Next, K2 FeCN6. In this case, both of them are +2. So here also it is +2, here also it is +2. Here also it is +3, here also it is +3. Or inside outside is +3 and +4. Correct? So like K FeCN6. So outside is +3, inside is +4. Sorry, +2. This way. Correct? Or lastly, if you have uh, uh, no, earlier I think I have written it already. F4 and so those cases. Okay. Yeah, if you write it like this, Fe4 FeCN6 thrice. This is the form which you have right now. Clear? Now, what are these exactly? See, what are the colors they also have? Going ahead, this will be very useful here. Check. When you have one of them being +3, the other one being +2. This is the case now. Okay. The first one, both Fe +3 and +3. Whenever there is an iron +3 and +3, both of them are +3, right? In that case, the color will always be brown. Always. Remember that. It will always be brown. If iron is both +2 and +2, the color is always white. irrespective of whatever the ligand you are talking about. They'll usually be white. Next, if it is plus 3 plus 2 or plus 2 plus 3, either ways, inside, outside, anything. In that case, the color, the first case color, when you have Fe cyanide, this one, this is called, okay, turns, uh, turn bulls, turn bulls blue, turn bulls blue. Okay. In fact, this is also called as, this is also called as uh, Prussian blue. This is also called as Prussian blue. But there is one slight difference here. That is, when you are talking about inside and outside, right? Suppose I'll change this part here. If the outside part is plus 3, outside part is plus 2, and the inside part is plus 3, then it is called Turnbull's blue, correct? But if it is the other way around, that is, outside part is plus 3 and inside part is plus 2, then we call these two are, in fact, these two are one and the same. These two are called as Prussian blue. Prussian blue. So without oxidation state, we cannot differentiate everybody. Okay, without oxidation state, we cannot differentiate. If the oxidation state given only, then we can say, huh. But if this kind of case is given, that means it is definitely sure that it is Prussian blue. All good. Okay. Next, let me finish this colored part. Next, color is also formed due to delocalization. Okay, color formation due to delocalization. Okay, okay. For example, if I take two isomers, naphthalene, this is a naphthalene form, naphthalene, and you may remember that naphthalene has some conjugated structures, correct? In fact, three of them like this. So, what are the conjugated structures for the naphthalene here? One is like this, correct? One is like this, correct? One is like this. These are the resonating structures. So you can see there is an extension of conjugation, but both rings are both rings in all resoforms. Thank you. In resostructures, resostructures are okay, are benzenoid forms. Benzenoid forms. Benzenoid forms means, see, every time you see the rings are of benzene kind, correct? At least one ring you can see they are benzenoid form. So when you have rings more benzenoid form, then you'll hardly see any color, correct? So then means more the benzenoid form, more benzenoid forms, less color observed, less color observed. Okay, clear. But if I take the same naphthalene's isomer, which is azulene, this is azulene, correct? 7 and 5 member ring together. Okay, so its structure is supposed to be like this way, this one, azulene. Azulene will have very high delocalization like this. Okay. Come. All right. Azulene will have high delocalization like this. That is this way. Okay. So you can see double bond, double bond, double bond with positive charge here, double bond and negative charge. Okay. So you can see none of them are benzene forms, right? So this is the most stable resonating forms also. This is the most stable resonating form also. So in such case, this will be colored. Okay. So whenever you have more extension of conjugation and less benzenoid forms, they will be usually colored. Okay. Let me show some compounds here. Some compounds, some compounds with high conjugation, extended conjugation, sorry, high extended conjugation. Okay. So extended conjugation is observed in these cases. For example, here we have benzene form here, double bond. Then let me write on this benzene form here like this way. Then we have N, double bond N, correct? On the other side also, we have benzene form like this, connected with S, double bond O, and O minus Na plus here like this, correct? And then we have N and methyl, correct? Even if you have such long, uh, long range of conjugations, then also molecules will be colored. In fact, this is what is methyl orange, if you remember. Methyl orange. And methyl orange is colored. In fact, this is in a basic form. Basic form, what is the color? In basic form, it is yellow color. Correct. In acidic form, what is the color? Red color. Okay. Here, everybody. Same goes with phenolphthalein also. Phenolphthalein will also show color because of its conjugation. Okay. So I hope all of you got some idea about how the colors are. You know, what is a color wheel, how the charge transfer happens. So these are some important fundamentals you need to learn from complexes point of view. Okay, right.